Oopsie. Okay. Good morning, everyone. Welcome to lecture 15. Okay, last time we started talking about flow problems. We introduced the notion of a network, which is a graph with capacities labeled on the edges and also a distinguished source and a distinguished sink. We saw how to solve max flow by reducing it to linear programming. And in turn, because linear programming has a general polynomial time algorithm that gives us a way to solve the max flow problem. But then we went beyond that and we came up with a direct algorithm based on augmenting paths in a residual network that gave us a more efficient direct solution. And the correctness of that algorithm relies on this max flow min cut theorem, which I'm going to write again. It's a very important theorem to remember. So the max of the value of a flow in a network, okay, is equal to the minimum across all cuts of the capacity of the cut. And of course, both flows and cuts are taken with respect to the same ST, right? So the same source and the same sink. Like a flow is always with respect to a source and a sink, and so is a cut, okay? Okay, so today we're gonna kind of talk about something I was only briefly mentioned last time, which is this notion of duality in linear programming. And the max flow min cut theorem is an example of duality in a very particular case, the setting of max flows and min cuts. But in general, for any linear program, we're going to see we can define a corresponding dual, and you're going to have some similar behavior where the optimum of the original program, if it exists, it equals the minimum of the dual program. We will not, it will be primarily example driven with some general discussions, but we will not be proving the duality in its full generality. That's something that if you're interested, you can look up for yourself. In any event, let's talk about some intuition. Why is duality a phenomenon that may hold in general? So let's talk about some specific example with no particular interesting structure. This is it's not related to network flow or anything like that. I copied here the example that we saw 2 lectures ago when we first started talking about linear programming, okay? So here's the linear program. We wanted to maximize this bivariate linear function subject to both variables being non-zero, x1 at most 50, x2 at most 80, and the sum of the two being at most 100. And we rather carefully went through drawing in the real plane the solution to the linear program. Remember that each of these constraints, linear inequalities, gives us a half plane. So non-negativity puts us here. Then these two guys correspond to this side of this plane and this side of this plane. And the sum of the two gives us this diagonal over here. The objective function itself is a vector, right? So because the coefficients are 2 and 4, here we have this vector that is 2 and 4. And the maximum is pushing as far away as possible in this direction, which takes us to this vertex here. And remember, we already talked about the fact that we have this high dimensional polytope. And if there is a feasible solution, and it's bounded, then in particular one can take it to be a vertices of the polytope, one of the vertices of the polytope. So in this case, the solution was x1 and x2 equals to 20 and 80, right? Because this one over here was at x1 equals 2. And 1, 2, 3, 4, 5, 6, 7, 8. So that's x2 equals 8 with a value that is 2 times 20 plus 4 times 80, which is 360. All right. Okay. And we kind of eyeballed this solution. Now we can actually with some pretty simple computation, we can actually prove that this value is optimal, okay? So what we're going to do is we're going to manipulate these constraints, okay, to show that any feasible solution to this problem, to this program, must be at most 360. Okay, that somehow there is, like, these constraints imply that any feasible solution must be at a value at most 360. And because we did find a solution that has value 360, then we know it must be the maximum. Okay, so let's do that. So how are we going to manipulate these? So we're going to use this notation that I'm going to write in parentheses the constraint. I'm going to put a coefficient in front of it. I'm going to add up these constraints. Okay. So let me write here all the constraints. And for now, I'm just going to pull out some coefficients out of a magic hat, and then we'll kind of see how to systematically derive them. So say that I multiply the first constraint by 0, the second one by 2, and the third one by 2. Then what I'm going to get is another kind of inequality. Now, on the right-hand side, I'm going to get 0 times 50 plus 2 times 80 plus 2 times 100, which coincidentally equals 360. And on the left-hand side, I'm going to get 0 times x1 plus 2 times x2 plus, I don't have space, let me move this, plus 2 times x1 plus x2, okay, which also coincidentally equals the objective function, right? So what I've done here is to just say, well, all these constraints these constraints must always hold. Let's see some implication of these constraints. And so I multiply the first one by 0, the second one by 2 and 2, right? And I derive anything that satisfies these things must also satisfy this inequality, right? I can just add up these inequalities, right? And what we see here is that we have learned that 2x1 plus 4x2 must be at most 360. And we haven't, like, this is an arbitrary x1 and x2 that satisfies the constraints. But look, we have already found a particular x1 and x2 that achieves 360. So that must be the optimum, because we have already just derived that anything that satisfies the constraints must in particular have value at most 360. Okay? So now, again, these constraints here, I mean, these coefficients here look magical for now. We'll talk about for a moment how we derive them. But is it clear that with this local manipulation, we have proved, like, algebraically, that this particular feasible solution is optimal? I hope that makes sense. Right, I take the constraints and I infer some other inequality that is implied. Okay. All right, I don't see any questions, so it seems like this is clear. Okay, but you know, maybe we don't have a magic hat. How do we pull out these coefficients, right? So how can we systematically figure out how this optimality certificate, where would it come from? Okay. All right, well, let's try to kind of take a step back and systematize our approach to that particular example, to somehow mechanically derive what those coefficients ought to be. So in general, this 0, 2, and 2 were just some variables that I eventually need to set, right? So let's give them a name. We're going to introduce variables y1, y2, and y3. And we're going to consider a generic expression, which is y1 times the first constraint, y2 times the second constraint, and y3 times the third constraint. Now, a small delicate thing here is that I am multiplying inequalities. And in order for them not to flip, I need the coefficients that I'm multiplying by to be non-negative. Otherwise, they flip. Okay? Like if I multiply by -1, then inequality will flip, right? It's okay to multiply by 0 or 1 or like a half, something like that, right? So I'm going to introduce these three variables, and for now, I'm just going to say they're non-negative. All right? And now I can generically try to see what expression I get by multiplying the first coefficient by that generic variable, and so on and so forth. So if I sum up these three constraints, on the right-hand side, it's pretty clear what I'm going to get. I'm going to get 50 times y1, 80 times y2, and 100 times y3. Right? That's what I get on the right-hand side. On the left-hand side, I'm going to add up things and collect by x. Okay? So x1 has a coefficient y3 and y1, right? So I'm going to write y1 plus y3 times x1. And x2 has coefficient y2 and y3, right? So I'm going to write y2 plus y3 times x2. Now, our goal was for the left-hand side to represent our objective function, which, remember, I have copied it here, was 2x1 plus 4x2, right? So whatever y1 and y2 and y3 are, I would like them to be such that this sum equals 2 and this sum equals 4, right? Because I'm recreating here the objective function. So this is to match the objective function, right? And actually, I don't really need it to be 2 and 4. Since I'm maximizing, it's okay if I just ask at least 2 and at least 4, because even more so if 2x1 plus x2, like if I want to bound 2x1 plus 4x2 from above, it suffices for me to upper bound anything above that, okay? With coefficient at least 2 in x1 and at least 4 in x2, okay? And again, these things are non-negative, right? So this is also okay. So in sum, what we have learned here is that 2x1 plus 4x2 is going to be at most 50y1 plus 80y2 plus 100y3 whenever, at least when y1, y2, and y3 are non-zero, y1 plus y3 is at least 2, and y2 plus y3 is at least 4. So for any variables y that satisfy these constraints, it is the case that 2x1 plus 4x2 is going to be at most this quantity. Okay? Now, because I want the best upper bound, I'm actually interested in minimizing this expression in y, right? Because these coefficients y, I want the best upper bound so that I can actually get the maximum, right? So I'm going to want to pick this y1 and y2 and y3 to minimize the right-hand side, right? Because up here, if I had chosen, I don't know, like 1,000,000, 1,000, and like 1,000,000, I would get an enormous upper bound that I'm not interested in. Like, who cares about learning that 2x1 plus 4x2 is at most, I don't know, 10 million? I don't care. I was interested in specifically making it the best upper bound that I can, because that thing is going to match, ideally, the maximum. Okay, well, we don't know yet what it's going to match, but that's the best I can hope for, right? So then the best coefficients that I can put for are whatever I can minimize. Let me minimize this given these constraints. But look, that's a linear function. These are linear constraints. We have another LP. This is called the dual LP. We can write it. So what we want to do is want to minimize 50y1 plus 80y2 plus 100 y3, subject to y1, y2, y3 being non-negative, and y1 plus y3 being at least 2, and y2 plus y3 being at least 4. The solution to this linear program is going to give us a certificate of optimality for the original program we started with. Oopsie. This one over here, okay? Then one solution to that one that is optimal is this one. So, and in this case, not only was it an upper bound, but it actually matched. So in other words, if we have solutions to the primal LP and the dual LP that have the same value, then they are both optimal. In our case, x1 and x2 being 20 and 80, and y1, y2, y3 being 0, 2, 2, they both have values 360, right? We can see it here. If I put 0 here, and 2 here, and 2 here, I get 360, which is the same value that I got, all right? So what we have done is that we took the particular example, and we have systematized the finding of an optimality certificate, and systematizing that gave rise to another linear program, this one, which is the dual of the program we started with, okay? All right, maybe ask if there are questions so far. This is basically how one can find this one over here, okay? The optimality certificate. So there's a question about whether they both have to be optimal. A priori, now we have no reason to believe that they both have to be optimal. Maybe there's a gap between them. Let's kind of go back to maybe the case of max flow and mean cut, right? We eventually proved the quality, but before we proved the quality, we proved that the max flow is at most the mean cut. Proving that they're equal is an extra property that held in that case. And it turns out that actually holds in every case. We will not prove that in class, but it is a general phenomenon that the primal and the dual, if the primal is feasible, then the dual is also feasible. Sorry, if the primal is feasible and it is bounded, like it has a maximum, then the dual is also feasible and it has a minimum, and the maximum and minimum, they agree. Okay, that's exactly what's happening here. So the picture you should have in mind, or the intuition you should have in mind, is exactly what happens in the max flow mean cut theorem. Okay, that kind of mean cuts are like the dual of the max flows. And because they agree, then that gives us this optimality certificate, right? Because if here we would have gotten, I don't know, 370, we wouldn't necessarily know that this was optimal. But because we specifically got 360, then we know that it is optimal. So it's an optimality certificate. Any other questions? Okay, seems like all clear. Either people are still sleeping or it's exceedingly clear today. What we're going to do now, something which is a lot of fun, being sarcastic, is we're trying to go one more layer of generality. And rather than systematizing the approach for a particular example, we're going to systematize the approach for any example. So we're going to take a general linear program, and we're going to try to infer what its dual looks like. This is something that we do only once, and then you know what the answer is, and when you take the dual, you just can apply that, right? But this is kind of trying to come up with what the dual ought to be. Okay? So we're going to do that. So first we have to write a generic a primal LP. So let's do that. So we're going to maximize some number of, some objective function. In this case, we're going to call it k variables. So here we have generic coefficients C1, C2, blah, 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 up to Ck, right? So this is a general objective function. We also have to write some general constraints. But we actually are going to categorize the constraints into 3 classes because we're going to operate on them differently, okay? First, we're going to have constraints that I call, that I call big I. That stands for inequality, right? They're constraints that look like this: AI1 times x1 plus blah, 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 up to AIK, xk is at most BI, right? This is a general inequality. We have some number of them. Whatever those are, just put them in a set and index them accordingly, and you have some corresponding coefficients, okay? All right, so that's one type of general constraint. Then we have big E. What is E? For equality. So it's basically the same thing, AI1, x1 plus blah, 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 up to AIK, xk equals BI, okay? This is the equalities, the linear equalities. And then there is big N, which stands for non-negative. And some, but not necessarily all, of the X variables are required to be non-negative. Maybe none of them, maybe all of them. I don't know. In general, it's going to be some set that says which ones. So we write xj non-negative. Okay? So, and I'm going to call M, the number of constraints, to be just these two, okay? And I'm kind of going to count separately what happens to the non-negativity constraints. But otherwise, all we have done is write a general prime and linear program, okay? We have the linear objective function, we have linear inequalities, linear equalities, and non-negativity constraints. All right. That was just for specifying the starting point. Now we want to do some reasoning that is kind of similar to what we did here to derive the corresponding linear program. Okay? So we're going to introduce y variables to correspond to generic coefficients in front of our constraints. Okay? And so here is yi, some generic yi, to multiply this coefficient, this constraint, this linear inequality. And so that we don't flip an inequality, we have at minimum to assume, or at least to constrain yi to be non-negative. Okay? Now we also have equalities, and for those, we actually don't care about flipping. So we're actually going to leave yi to be anything. So you may wonder, wait a second, why don't we still constrain yi to be non-negative? That can't hurt. Yeah, but the point here is that we want to introduce the minimal number of constraints to imply the upper bound. We want to try to be as stingy as possible with our constraints. We want to make only the absolute minimum necessary, because otherwise we may risk the new linear program and the original program to kind of detach and not meet at the maximum and the minimum, okay? So we want to kind of only write down the things that are strictly necessary for us to imply the best upper bound. So here, because I don't have to worry about flipping, I'm not going to constrain the variable to be non-negative, okay? Okay, great. Then, and so this was analogous to what we did up here, except that up here we only had linear inequalities and we didn't have the case of linear equalities. And so now we just are also handling that case, okay? Now, what did we do next here? Well, we wrote to the right-hand side, and we wrote on the left-hand side collecting by x, all right? Now, here, we are going to still collect by x, but we're going to distinguish whether x is going to be non-negative or not. All right? So let's start with x that can be non-negative. So we collect by x that is non-negative, so we have this xj, and here we need to write down all the y's that participate with xj. Well, who are they? Well, it is the sum for I in the union of I and E, right? Because xj may appear here or here, right? And so it will pick up this coefficient or this coefficient for I in I or I in E, right? Times aij yi, right? And I'm going to want this to be at least Cj. Who is Cj? It is the coefficient of xj in the objective function. Okay? I also have the other xj's to deal with. The xj can still appear here or here. So I'm still going to write sum of I in I or E, aij, yj. But now, xj could be negative. And so it is not the case anymore that it holds even more so if I make the coefficient bigger. It might hurt me. So here, I really have to specifically write equal to Cj. I cannot afford the relaxation from equal to xj to at least, to equal to Cj to at least Cj, because I don't know whether xj will be positive or negative. So I really have to be on the nose on the coefficient Cj. Great. On the right-hand side, well, we summed up we have the y's in I and the y's in E, and they come with the coefficients bi and bi, right? So we're going to sum over small I in big I, bi times yi, and over I in big E, bi times yi. That's what we get on the right side. Okay? So we have kind of written down what we get by summing up things and keeping track of what we want to happen in order for this to be, like, for this expression to be an upper bound to this one. Okay? And like before, since we haven't really oopsie, so there is one, it should not be yj, apologies. That's not, that should be yi. Sorry about that. Good catch. And like before, we want to get the best upper bound, so we're going to want to minimize the variables y subject to certain constraints. Okay? So now we're about to write the linear program. Let me just summarize. What we've done is one multiplier variable per primal constraint, there and there. One constraint per primal variable. Here is the constraint, right? And then we want to minimize the induced right-hand side of the sum, this one, right? So we're going to do it now. Let me just keep it like this so we have good state. We're going to minimize b1, y1 plus up to bm, ym. Okay, this is basically, I'm kind of, anyways, so everything in I and everything in E, I had defined to be m, right? So I'm just, this thing over here, I'm just writing this way, okay? Subject to something. Well, for j in the non-negative set, we can write this expression has to be at least Cj, okay? So let's write it. We're going to write a1j y1 plus all the way up to a mj ym should be at least Cj. Then for j not in a non-negative, the same expression, but with an equal sign. So let's write it again. I'm going to copy it, and I'm going to change just that one symbol, equals Cj, right? And then we also said that certain y's have to be non-negative. Which ones? The ones specifically in the set big I. Therefore, we're going to write yi as being non-negative for little I being in big I. Okay? And we have written the dual. Okay? So I have just shown you a recipe to write the dual for any linear programmer you will encounter. Okay? And you can either like memorize it, or you can rederive it this way, which is not bad, right? You're just trying to basically infer the minimal constraints necessary to impose the best upper bound. Okay. Now there's a special case that is worth remembering, that is quite easy to remember. If all the constraints are inequalities, like no equalities, like no equal signs, and all the variables are non-negative, then the relationship between a primal and dual is very easy to summarize. So if I want to maximize this linear expression, sum of C1 x1, C2 x2 up to Ck xk, subject to Ax is at most B, and all of x is at least is non-negative, and here x, it's a vector, right? Okay, and B is also vector. Then the dual is going to be, you just take the B and you put it up here, okay? And what you're going to do is going to minimize the inner product of B and Y are the new variables. And here write A transpose Y is at least C, and then Y is greater than or equal to 0. Why the transpose? But we can see it up here. Like over here, we are kind of going by, you can think about it, what changes in the constraint is the column, right? We're changing, like, sorry, not is the row, right? The same J, which means the same column, but we're changing row. A1J, A2J, blah, 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 up to AMJ, right? We're changing by row, right? But up here, we're changing by column. We're fixing a row, I, and changing column 1, 2, 3, blah, 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 right? So in going from here to here, we took the transpose, right? And that's indeed what's happening here. We take the transpose over the coefficients, and what used to be the variables and the constraints are switched. Now we have the number of constraints now is number of variables, the number of variables now is the number of constraints, which is exactly what happens here, right? By transposing the matrix, whatever was the variables are now the constraints, and whatever was the constraints are now the variables, okay? So in this case, the primal and dual have a very simple relationship that is kind of very easy to remember, okay? But this is not the full general case. In the full general cases up here, which is slightly more, I wouldn't say annoying, but just less easy to summarize. All right. There is a question about whether we apply the dual transform twice, do we get back to the primal form? Yes, you may not get the exact same form, but you will get the same linear program. Like I don't know whether you're going to get like literally the same thing, but you're going to get something equivalent to it with the same feasible solution space and the same maximum. Okay, because sometimes you have different equivalent representations of a linear program, right? All right, and so here what we've done is we have systematized for the general case how you infer the dual. Okay, now actually before I continue, let's see if there are any other questions about this transformation. All right, can explain a bit more the difference between these two, right? So let's go up to the example first. Now, we started out by saying, okay, look, we want to derive an upper bound on this expression, 2x1 plus 4x2. So a first guess would be to say, okay, I'm just going to set y1 plus y3 to be 2, so that I match this coefficient, and y2 to be plus y3 to be 4, so I match this coefficient. But really, because x1 and x2 are non-negative, like they are non-negative, where do you go? Here. it is sufficient, but not necessary for these things to equal 4. It could be, it's enough to just have them at least being 2 and at least being 4, right? Because if you know, let me give an example, that let's say 5x1 plus 6x2, no, sorry, yeah, 5x1 plus 6x2 is at most 360. Because x1 and x2 are non-negative, that is certainly the case that is an upper bound for 2x1 and 4x2, right? Because with those bigger coefficients, you can only get something bigger, right? So it doesn't mean that it's useful, but it's okay to consider it as a reasonable like upper bound, right? So in this case, because we're looking to write down the minimal constraints necessary to get an upper bound, it's okay to write at least 2 and at least 4. Like it won't hurt, right? But when we don't know whether x is positive or negative, we cannot afford to relax this constraint to be at least Cj, because if x had been negative, xj had been negative, it would not have been a valid upper bound. It may have gone below where we should have been, okay? And so here we specifically must hit the coefficient on the nodes, okay? All right, good question. Any further questions? The question, but why didn't you say xj is at least 0? No, we didn't say that. We said xj is at least 0 only for things in a specific set, right? So out of these xj's, only things in N have this property. And that's why for things not having that property, we set the coefficient to be Cj. Let's see, any further questions? Good, all right. So now you have a recipe to take the dual in general. What's the property of a dual? Well, it's this duality theorem, okay? It's some sense, rather deep fact. It's like not obvious a priori. It's also extremely useful. That says if the primal linear program has a bounded maximum, okay, then the dual will also have a bounded minimum, and the two values are equal, okay? So that pictorially, what you want to think about is that there is some feasible space. There are some feasible solutions. Oopsie, I want to start from the other side. There are some feasible solutions for the primal linear program. And at some point, you're going to hit the maximum, okay? Because we're saying if there is a bounded maximum, right? So there's a primal optimal, right? That is the maximum. That's the maximum we can ever achieve. And on the other side, we have the feasible solutions for the dual LP. Not all of them equal the maximum, of course, only the dual optimal, okay? And like the analogy here is that every flow is bounded from above by a cut, or rather the value of a flow, of any flow is bounded from above the capacity of any cut. And specifically, the maximum flow has the same value as the capacity of the minimum cut. They meet in the middle here, okay? Now, what happens if the primal is unbounded? Well, they cannot meet because it's unbounded. It's as if kind of this middle point is not there, it just goes all the way to infinity. In that case, the dual will be infeasible, okay? It just doesn't have any solution, because if it had any solution, that would be a valid upper bound on the primal, but the primal doesn't have an upper bound, it's just going to infinity, okay? All right, so this is kind of the picture you have. And as I said, we will not prove this duality theorem. In fact, what I stated is really strong duality. There are two theorems: duality that says that the dual linear program is an upper bound, and strong duality says that not only it's an upper bound, but it equals the maximum of the primal, okay? And I wouldn't say like proving it requires very deep ideas, but it requires some careful manipulations of general expressions. And if you're interested, you can look it up. There are sort of, you can find it in books or lecture notes. From the perspective of this course, we'll not talk about the proof of this theorem. We'll just kind of use it as a black box or as a true statement. Okay, and so make sure that you're familiar with it. The only kind of operational thing that you will be asked to understand for linear programs is formulate linear programs for problems and taking duals of them, right, using the recipe that we talked about. But again, we're not going to be proving it. That though, for those of you that are interested, I certainly encourage you to learn more about it, because it's a very important fact about. Also, if you're interested in optimization, this is kind of like the first non-trivial thing that you learn about optimization. In this case, linear optimization. Okay, any questions about what the theorem means? Okay, well, I'm going through this lecture much faster than I expected, so I'm going to finish a little bit earlier. All right, so let's talk about an example of duality. This is like really straight from the book. I think it's a very cool, sort of observation. We can actually try to think of duality in some physical terms, which is like pretty astonishing. So for certain examples. So let's consider a problem, shortest paths, but differently from how we talked about shortest paths earlier in this course. Rather than starting from one vertex to anywhere else, I'm going to specifically focus on one vertex to another vertex. Okay, so we are interested in computing the shortest path from S to T. All right, and we're going to be in an undirected graph with positive lengths. Okay, now one way to solve this problem is to say, I have Dijkstra, let's run it. Okay, so we could use Dijkstra's algorithm. It's true that we don't want to compute the distance to every other node, but we're specifically interested in one of them. But we really have to compute the rest, kind of, at least for Dijkstra, right? It could be maybe other nodes are useful. So yeah. So here's an alternative way to solve the problem. We're going to think of a physical model where you have V balls, like V being the vertex set, and they're connected according to the edge set E via strings, like loose strings. Okay, and each string will be measured according, like each string from U to V will be measured according to the length of the edge. Okay, so the picture to have in mind is you have kind of this graph, right, with like physical balls, and you kind of measure strings between them according to the correct lengths. And one way to compute the shortest path from S to T can be visualized as basically, let's say that this is S and that's T. Okay, you can basically pull away that ball away from T, okay, until you cannot pull away any longer. Okay, now intuitively, the first sequence of strings to become taut will be the shortest path from S to T, right? Like you take the ball S and you pull it away from T, right? And think of T as being anchored somewhere, so it just doesn't move around. And the first sequence of strings to be taut from S to T will be precisely the shortest path from S to T. Okay, so let me write it down. You're gonna pull S away from T until no longer possible. All right. Now, and you say, okay, fine, thank you for the physical experiment. What's the point? What's interesting is that this pulling away is maximizing distance when we're trying to solve a shortest path, which is about minimization. This smells like dual, right? So what this physical model is doing is solving the dual program. We can actually write down the dual program for this problem and argue that it actually is solving the shortest path problem. So let me say it precisely. So we are solving the dual LP of shortest paths. Okay, let's write the dual. We are going to minimize a variable xt. Okay. Oh yeah, sorry, taking a step back. We introduce one variable per vertex. Okay, those are the variables in the LP. Only one variable is going to be in the objective function, the one corresponding to the vertex t. So we're going to maximize xt subject to certain constraints. Well, first, we want to say that x for the source is 0. Okay, that sounds reasonable because anyways, the distance from S to S is 0. And then for every edge, we're going to say, look, the farther edge xv cannot be further than where xu is plus the length of the string. Right? So if I want to pull away v from u, wherever u is, because the length of the string is luv, v cannot be farther than that thing plus luv. Okay? So this linear program is precisely capturing this thing. All right, but that's just intuition. Let's actually prove that. Let's prove that the optimum for this program is such that it has precisely the distance from S to T. Okay, so that we can prove. Actually, before I prove that, is it clear what the intuition behind the linear program is? Like, it really does kind of capture this pulling away thing, right? I guess, maybe, sorry, more precisely, I should be thinking about pulling away xt, right? So pulling away t. That's, we're increasing. You can think about it as there is xs equals 0, and we're kind of pulling away, like maximizing xt is like pulling away the ball t away from s, right? There's a question about can you clarify what is xt? So the variables in our problem are xv for v in v, right? So we're introducing one variable per vertex. In general, an objective function can be any linear combination of these. For the linear program at hand, all of them have coefficient 0 but 1, specifically the variable xt, which is associated to the t vertex, this one over here, okay? And since we're thinking that s stays put and we're pulling away xt, subject to the physical constraints of the strings, because of that, we're going to fix xs to be 0 and enable any ball to move at most LUV away from the previous ball, right? And at some point, what does xt have to do with UV? Well, some of the vertices, some of the edges are going to have t here, right? So it will appear somewhere here, right? So here is, we're saying for every UV in E, in particular, one day when we go over all E's, one of those edges will be this one, okay? And then in that case, xv is going to be xt. And xt represents the distance of this ball from the original ball, right? So this is like distance 0, and we're moving in that direction, right? And of course here, really, I should kind of squash it all down on the line so that we don't have a second dimension, but we're kind of pulling out in that direction. Anyways, this is all just English and pictures. Let's prove that the answer is correct, right? So at the end of the day, this is a linear program. It's well-defined, and I can prove whether the optimum has the correct answer, right? So let's do that. First, I want to argue that the optimum, whatever it is at least the distance from S to T. One way to show that is that I can assign the variables in such a way that this holds. How? Well, how about I assign them by setting xv to be the distance from S to V. So for every V, I set the variable xv to be the shortest distance from S to V. And now we need to ask ourselves, is it feasible? And does this hold? Well, look, xt is one of these, and it is distance from S to T. So the optimum, whatever it is at least that, right? And then we need to make sure it's feasible. Well, the distance from S to S is 0, so this is fine. And the distance from S, let's kind of view it like this. So I have some edge U, V, and the distance from S to U is, sorry, the distance from S to V, like in some path here, right? Or I don't know how it goes, but there's distance from S to V, is certainly no more than the distance from S to U plus the edge from U to V, because that is one of the options for me to go to V. And the shortest distance cannot be more than that, right? So therefore, setting variables this way shows me that the optimum is at least the distance from S to T. Okay? That's not enough. I am claiming that the optimum, oopsie, that the optimum here is precisely equal to the distance from S to T, that this linear program precisely lets me compute the distance from S to T. So I need to prove the other side of an inequality, that the optimum is such that it is at most the distance from S to T. Okay, let's do that. Consider any path that goes from S to T that has optimal length. Let it be this path over here. Okay, so goes from S to V1 to blah, 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 Vk, and at some point T. And this one has length that is distance S to T. One of them must exist, right? Because the distance from S to T is realized by some path at least. I know that if I take this path, let's just basically this path gives me some suggestions about which variables to consider. So let's take these variables and write a set of constraints implied by these that will let me infer something. So what am I going to pick? I'm going to pick xs equals 0. Why? Because s is here. Then, because I go from S to V1, I'm going to write the constraint xv1 is at most xs plus L from S to V1. Where does this constraint come from? Well, it's one of these. So I can write it down, like it clearly holds, right? Then, because I'm going from V1 to V2, I can write the constraint. I mean, among all the constraints I can write, I can in particular write the constraint xv2 is at most xv1 plus L from V1 to V2. And I continue in this fashion. And if I add up all these inequalities, I will have a telescoping sum. Why? Because look, when I add them all up, xs and xs cancel. xv1 and xv1 are going to cancel. And xv2 and v2 are going to cancel. I'm just going to be left on the left-hand side with xt, which is the last one that doesn't appear twice. And on the right-hand side, what will I have? Well, I will have L from S to V1 plus L from V1 to V2 plus L from V2 to V3 and so on and so forth, right? But what is that? That's just the length of the path that I have, which precisely equals the distance from S to T. So I've derived an upper bound. And since I derived an upper bound and a lower bound, I can only conclude, like I am able to conclude that the optimum is precisely this distance. Okay, so whether you believe the physical analogy or not, this claim is going to tell you that this simple linear program is solving the problem of computing the shortest distance from S to T. Questions? I see there are like a variety of questions earlier about this one, but hopefully some of them have been clarified by this claim. So let me know if there's still something left open. How did we telescope the sum? Well, if I sum this one and this one and this one and all of them, I will have, okay, and you can think of, one way you can think about the first one is, let's say XS is at most 0 in particular, that's certainly the case, right? If I sum this inequality with this inequality and this inequality, right? And I add them all up, right? I will have a bunch of things on the left and a bunch of things on the right, right? Things that appear on the left and on the right, they just go away, right? So XS will appear on the left and on the right, so I can cancel it. XV1 will appear on the left and on the right, so I can cancel that too. The only thing that I won't be able to cancel is XT, because it appears just in the last inequality on the left. So it stays on the left. And then I'm left on the right with all the L's, right? And here they are. And the sum of the L's is precisely the length of the path, which is the distance from S to T, because we pick the path to be optimal. Okay? All right, so there's a question about this argument over here. How do I show that the maximum of a linear program is at least something? Well, it suffices to exhibit a feasible solution that is that something. Here it is. This is a candidate feasible solution whose value is precisely distance from, like when I fix V to be T, it has value distance from S to T, right? And I have to check, is it feasible? Well, let's see. Is this constraint satisfied? Sure, because XS will be set to the distance from S to S, which is 0. Great. Is the distance from S to V at most the distance from S to U plus LUV? Yeah, sure, because one way to go from S to V is to go through U first and then take this edge. So all the constraints are satisfied, and I know that the maximum must be at least that. Any further questions about this slide? There's a question, how do we know that that one is the optimal one? Because we picked this path to be a path with length st, right? So this is not any path. This is a path that has optimal length. And I can pick it, it exists, right? So here, all I wanted to do was to kind of infer some upper bound, and can do it whichever way you want. And in particular, we can do it this way. Okay, so we went through a lecture a bit faster than expected, so we're gonna finish a little bit earlier. I can, of course, stick around for more questions, but either way, maybe it's okay that we finish a bit earlier today, because last time I felt like it was maybe a bit of a kind of packed lecture. So I'm going to stop now the recording.